We welcome to the next lecture on process control analysis, design and assessment. So, today we are going to look at various methods that are used for stability analysis. So, here are some of the methods that are generally used for stability analysis. One is route array, other is root locus and frequency analysis based stability analysis, and then we will briefly look at these methods. We will not go into much detail into these methods. And then you will also understand see everything is like stability analysis of the same system. So, all these things are connected to each other. So, that is what we are trying to look at it in this, and then in the next lecture we will also see some example of Nyquist stability. So, from the lecture on what are the effects of PID gains on the closest like controllers response, we were able to observe this table. So, if you look at this table, one thing that is of interest is like from proportional controller there is an offset, that is a steady state error, and if there is a change in set point, and as and when we increase the value of the proportional gain Kp, the offset decreases. So, one natural question we might ask is like, why can't I increase this Kp, why can't I keep on increasing this Kp, and is there any problem associated with this? So, that is what we are trying to ask the question, and let us actually do this experiment again like we did in the previous lecture, and then we will see like what exactly happens and why what problem it is introducing. So, now we again we take a linear time invariant system which is of this form, g of s equal to 1 by s cube plus s square plus 2s plus 0.1. You can take any other system. Just for illustration purpose we are taking this particular system, and this is the MATLAB's simulating that we are showing. This is the control loop. Basically we are having a set point here, and we are trying to change the set point by a step change, and then this is the control loop, where this is the controller, and this is the system. System is nothing but 1 by s cube plus s square plus 2s plus 0.1, and we are going to see the value of the controlled variable in the scope. And what we are trying to do is basically we are going to do a servo response by changing the set point, how the control how the control variable is changing, whether it is following the set point change or how it is behaving is what we are going to see. So, when we have this controller as a P controller which is only Kp, and Ki and Kd equal to 0, where proportional gain is 0.8 here, integral gain is 0 here, and derivative gain is also 0 here. So, it is a P controller. So, basically when we give a step input, so this red line is the input. Basically this is how we want the control variable to change. So, set point, this is the set point, and this is how the controlled variable is actually behaving. So, basically if we can go back to the previous slide and see, this is the red line, and this is the blue line, how the response is basically. So, we can actually, if you want to relate it to a physical system, basically if I say I want to change the flow, for example I want to increase the flow by a step. For example, I want to go from say a flow value of 3 meter cube per second to 5 meter cube per second. This is how I want it to, I want the change to happen, but it is changing like this, basically something like that. You can flow, temperature, anything you can think of this, and then now again we ask the question, I want to decrease the offset. So, we can see clearly there is an offset here. So, I wanted the flow to go to 1, but it has gone only to up to a 0.9 or something. So, basically I want to decrease this, and we have seen that by increasing the value of Kp we can actually decrease this. So, evidently we can see this value has decreased when you compare to the previous thing, and now again we have increased Kp from 0.8 here and to 1.125 here, and we have seen a decrease in the offset. So, again why do not we increase it little more? So, let us make it as 2, Kp equal to 2, and then we see the response here. So, interestingly what happens here, this begins oscillating, the system goes unstable. Why it goes unstable? Because and as time increases the value it keeps oscillating, and the amplitude of oscillations is going to increase. So, basically if I can ask you a time equal to say 10,000, what will be the amplitude? It may be definitely like in terms of like some hundreds or even some thousands, etc. And also another thing we can see here is this is not a straight line, this is like a exponential increase. See, if it was a linear increase, if you could recollect, we saw a linear increase in the amplitude in when we have the concept of resonance, and in that what happened, we were actually having increasing amplitude even then when there were poles on the imaginary axis, and when we excite the system with the sinusoidal input of the same frequency, then this was actually a straight line. But now here you can see that it is not a straight line, which you can see here from, we will just see another value of Kp, and then we can confirm that it is exponential. Even here you can see clearly it is an exponential increase, not a linear increase. You cannot strip it a straight line here. If you had drawn a straight line, you would have come something like this, but still it is exponential increase. And another thing, okay, now what happened to our question of like, okay, increasing the Kp decreases the offset, what happened to that observation? Yeah, still we can observe that. If you could see here the mean of the oscillations, if you can take the mean of this oscillations, it will be closer to 1, or even it could be like equal to 1. So the mean of the oscillations is still like getting closer and closer to the set point value, but what happens is it just the output keeps on increasing and the system goes unstable. So this, if you could actually look into the partial fraction way of analysis, basically what it means is we have introduced a pole on right hand side of the. So basically if you can observe from the partial fraction thing, what you can say is we have introduced some term like e power lambda t and into a sine wave, into sine omega t plus some phi or something, and then this lambda is actually like a positive number. So amplitude of the sine wave is getting increasing with respect to the time. So when time increases, the amplitude also gets increased. So that is what we observed here. And now again, like to illustrate that it is an exponential increase, let us take Kp equal to 5. So basically now you can see this, you see the value of y axis, it is 10 power 12. So basically this is like in order of 10 power 12, 1 in 10 power 12, and all these are like, so basically you can see as time increases, the value is not increasing by equal amounts, it is increasing like exponentially. That is what you can clearly observe from this particular graph. And next we will ask the question like, okay, when we increase the Kp, at some point it system goes unstable. So though the question we can ask is like, okay, how do we find this value of Kp at which the system can go unstable? So that is what we are going to ask. And that is, before that question, if we are given a gain Kp, can you determine whether the system is stable or not? So that is another question, right? So first question we will ask is, okay, you give me a Kp, whether I can find whether the system is stable or not. So if I know the Kp, then what I am going to do, I am going to write the closed loop transfer function, and then I can actually split into partial fractions and then see if there is a pole on the right hand side of the S plane. So that if there is no pole on the right hand side of the S plane, then it basically means that there is no there is no problem of stability, that system is stable system. But like, okay, can instead of doing into all these partial fractions, instead of finding all the poles for a given Kp, is there any other easier way? So we can use this Rautheray stability. So in the Rautheray stability, what we can do is we can take a system, basically we will take Ga of S equal to some S cube plus S square plus 2S plus 0.1. So this is what we are going to take, and then here what we are going to do is let us take the control loop as we are giving a set point here, and then we are giving it to the controller, which is a P controller for now, and then this is given to the system, controller's output is given to the system, and then this is how the sensor is measuring the value of G of S here. So this is sensor value, and let us take the sensor is a unity transfer function. The sensor is actually just measuring it, and it has sensor has no lag, etc. So if a sensor has some lag, we are going to introduce the sensor function also here, but let us take for now sensor is a unity function, and then we will actually feed back the reading by the sensor back to the and subtract it from the set point. So basically this is C, and this is the error. Error is nothing but set point minus the value of the control variable as measured by the sensor, and then now this is a proportional controller, so we have only the Kp here. So now we can easily write the closed loop transfer function. Let us say C or okay, let us say the closed loop as CL equal to Kp into G by 1 plus Kp into G. So, this is what the closed loop transfer function is. So, now if we can find the value, what will be the closed loop transfer function, then it turns out to be, it will be like Kp by S cube plus S square plus 2s plus 0.1 plus Kp. So, now let us take this Kp to be some value. So, the question asked here is, given a Kp, can I, without resolving into partial fractions, can I find whether system is stable or not? So, that is what the question we asked. So, now when we say system, we can think like this is the full system. So, now you have a system which is a black box, you have a set point of system, and you are seeing the output, which is the value of the control variable. So, basically I am having a black box which is with the controller. So, I instruct the I give the input to the black box as the set point, and I observe like how the output of the black box is varying. That is what we are going to see. This is what, like, if you can see, if you can imagine, once we implemented all the control systems, what will basically have is, we want to change the input and then we want to see whether the output is following the input or not. We are inside of it, what happens to the control, how the controller is performing, all these things can be like, we will not focus much on that when if you have designed a proper controller, etc. So, basically you can imagine this particular box has become this black box, which is the control loop or something. So, this is what we are going to see now. So, this is the closed loop transfer function. So, this becomes CL block is nothing but it accepts the input as the set point and it gives output as the control variable itself. So, now let us take for now Kp equal to, randomly we will take one value, we will say 1 is a good number. So, we will take 1 as a Kp value, and then now let us find out whether this system is stable or not. So, to find whether the system is stable or not, I am going to just substitute the value of Kp here, and I am more concerned about the denominator. So, basically it becomes 1 by S cube plus S square plus 2s plus 1 dot 1. In the router table, like how you write S cube, S square, S and S power 0, which is 1, right. So, basically we take all the terms of S cube and S here. So, one coefficient of S cube is 1 and coefficient of S is 2 and coefficient of S square is 1 here, and coefficient S power 0 is 1 is like 1.1, constant term is 1.1. So, now the first term here, we are going to frame this term by cross multiplying this 2 minus cross multiplying this. So, this 1.1 divided by this term. So, 1. So, let us put this down here, okay. And so, what is the value of this? 2 minus 1.1 by 1, which is nothing but 0.9, right. So, 0.9. So, basically again this is nothing, this is here, there is no term to fill because there is no other terms left out here. So, this we will take it as 0. So, now basically you cross multiply this, subtract with this. So, subtraction is basically 0, right. So, basically what we get is 0.9 into 1.1 divided by 0.9. So, that basically becomes 1.1. So, everything this becomes 1.1. So, all the terms here are positive, there is no sign change basically, and that is not even a 0 here. So, basically all the terms here are positive. So, which means that system is stable, okay. So, when all the terms are of, there is no sign change in this column, then basically we say system is stable. So, definitely you can say system is stable. So, now as an exercise for you, you take the same system, you take the same thing, but just substitute Kp equal to 5 and then see whether that is a sign change here, okay. And yeah, you can see that basically you can try it for yourself, and also like try to find out whether there is a relation between the number of sign changes and the number of poles. Basically you can resolve into partial fraction again and then check out this. So, that will be an interesting exercise for you, it is a very simple thing. So, maybe you can do it as for yourself. So, basically what you do, you count the number of sign changes here and then see whether it and resolve this particular term into partial fractions, and then see whether there is some relationship between the number of poles on the right hand side of S plane and the number of sign changes here. So, what if we didn't have the value of Kp? So, that is what we are going to ask now. So maybe the question, maybe to put it in a different way, I want to ask like what will be the value of Kp at which system will go unstable. So in the lecture of the sir told like if you what will be the ultimate gain, that is what he asked the question. So that is the same question we are going to ask here. So the same exercise we are going to do. Basically what we had Kp by sq plus s square plus 2s plus 0.1 plus Kp. So this was the closed loop transfer function we got, and then we write this s cube, s square, s and s power 0. So this we add 1 and 2 here, and this we add 1 and 0.1 plus Kp, and now you put like 2 minus 0.1 plus Kp by 1. So without calculating s power 0 itself, we can say that if this is positive, if this term is positive here, and it is definitely positive because Kp is again, so this term will always be positive because what you are going to get here basically is 0.1 plus Kp into 2 minus 0.1 plus Kp by 2 minus 0.1 plus Kp, that is what you are going to get here. So basically if you can see here, this gets cancelled, whatever be the thing here, this gets cancelled, and this will be 0.1 plus Kp, and provided 2 minus 0.1 plus Kp is not 0, okay, then only then we can cancel this. So let us not bother much about this particular term for now. So the term which is of interest to us is basically 2 minus 0.1 plus Kp, and what we can tell about this is, if this is positive then system is stable, right, because we know if this is positive, this also s naught term also becomes s power 0 term also is positive, because like this is a positive term, not a 0 number, so this is cancelled, and 0.1 plus Kp is always a positive because Kp is a gain which is a positive number. And also one thing to remember is we are not trying to put a negative gain here. We are since it is a P controller, and let us for now take Kp only as positive values. So which is not that it's we cannot put Kp as a negative value, we can put, but no, for this case or for a P controller we do not normally put Kp as a negative value. So basically we will put Kp as a positive number. So basically now we can take like this particular term. So this particular term is the only term of interest. So for system to be stable, this term has to be greater than 0, okay. So this becomes like 1.9 minus Kp greater than 0, which means that Kp is less than 1.9. So first conclusion we can draw is whenever Kp is less than 1.9, this term is going to be, this particular system is going to be stable. So that's a straightforward thing we are going to see. If Kp is less than 1.9, this term is positive and this term is also positive, okay. So that's what we have seen in the first case, okay. So when Kp is equal to 1.9, what basically happens is we will see that the poles are on the imaginary axis, and we will see that a little later also. So basically now we have found the value of Kp when the system will go from being stable to unstable. That is the point where it's like as the sir told in his lectures, it's like the cliff in the tip of the cliff, right. So the Kp equal to 1.9 is like that gain at which the system transitions from an unstable system to an unstable system. So anything Kp greater than 1.9, it is going to go to unstable system. So now let us put this value of Kp into the system, into the control loop, which we simulate in MATLAB, and see what is the response. So this is how you get the response. So basically you get a sustained oscillations. So neither an increasing oscillation nor a decreasing damped oscillation. So you get a sustained oscillation, which means that this particular, when Kp is equal to 1.9, the poles are, this particular pole is on the imaginary axis. So we have a complex, so poles complex poles always occur in complex conjugates, okay. So basically you have two poles, and this is on the imaginary axis. So since it is on the imaginary axis, the if you take the partial fraction and then you take the inverse, it becomes like basically e power 0 into some sin omega t plus phi. So basically this is a constant one, so basically the amplitude is a constant one. Also remember, this initial transients we neglect, Okay. Whenever we talk about frequency response, the initial transient we neglect, this may be due to other poles. This is not the only pole we may have in system. This could be due to other poles. Other poles this transient is observed, and so. One more thing, so what are the observations we can make from this? When we increase the gain, okay, a stable system became an unstable system, which means that the pole has moved from the left half of the S plane to right half of the S plane, okay, and then so this makes us ask one question, right. So, okay, if we increase the gain and the closed loop poles are moving from left to the right, can we plot and then see like how these poles are moving? So, that may be one interesting question to ask. So, that plot where we plot the poles which is moving from left half of the S plane to the right of the S plane, that is called a root locus. So, root locus what it basically does is it plots the closed loop poles, okay. It plots the closed loop poles, because when the closed loop pole when all the closed loop poles was on the left half of S plane, the system was stable. When at least one pole moved to the right half of S plane, then what happens basically is like system became unstable. So, it plots the movement of closed loop poles when some parameter in here in sense we are interested in the gain. When gain increases, when the gain in the loop increases, then how the poles are moving, that is what the root locus is going to give us. So, we will not go into detail of how to construct these root locus etc. You can use MATLAB to plot this, and then basically you will see what is the how this root locus looks for the system that we are actually interested now. So, if you can see here, this is this system is a third order system. So, basically it has 3 poles, and one pole is here, one pole is here, and here another pole is there, and then the root these are, if you can see what are these values, these are all nothing but the poles of the open loop system. This is the open loop system. So, when we say open loop system, it is nothing but the G of S. System is open loop system, and then closed loop system means when we close the loop and then we found that G of S by 1 plus G of S, right. So, this is the closed loop system. So, this is the open loop and this is the closed loop system, okay. So, now this trajectory or these lines mark how these closed loop poles are changing. So, basically if you can resolve this denominator into fractions and find the roots of the denominator, so only it is called the root locus, how the roots move. If you can find the roots of this denominator, and you might recollect that denominator is also called characteristics polynomial, right. So, it is called the characteristic polynomial. So, how it is the roots of the characteristic polynomial, that is what it is going to show. So, and with respect to what, with respect to how the change in the gain is okay. Basically how the, if you change the gain, how it is going to change, how it is going to vary. So, when gain equal to 0, it starts when gain equal to 0, and then it goes like how if gain increases, how it is going to go. So, it is when gain increases, and this also when gain increases. So, basically clearly we can see that when gain increases, and here it moves like this basically. So, for these two particular poles, what we can see is basically whenever the gain increases, okay, the root locus is moving, the poles are moving towards the right half of the S plane, and there is a particular point, particular gain value when there is a particular point and particular gain value wherein the pole is actually meeting the imaginary axis, and that particular point, at that particular point, if you can see here, approximately the gain here is 1.9, okay, and see this is not exactly on imaginary axis. You can see this is like somewhat tilted towards the toward like 0.00437. So, so basically if you can plot exactly at this imaginary axis, if you can mark this pointer, it would basically say the gain is 1.9, and the frequency, the omega value, the y axis value is the frequency, right. So, and that y axis value is nothing but 1.4 something, okay. So, this is what the root locus is. So, basically it can show you how the poles are moving, and so this gives us two things. One is the frequency at which the frequency at which the poles are crossing the imaginary axis, which is the y value at which it is crossing the imaginary axis, and then the gain at which you can it is going to go from the left of S plane to the right of S plane. So, this is a root locus thing. And there are some things that you can try for yourself. This is mostly taught in like a standard like control course, but let us not focus on all these things much, because we are see, when we read with whatever content that is being taken in this course, without even root locus you can actually solve the problem. So, this is just another method that you can just know, that is what. So, we are not going to go into detail of how we are going to calculate all this, how we are going to plot all these values. So, but something like to just have fun with root locus, you can just observe certain things basically. So, root locus starts at open loop poles and ends at open loop zeros. So, why it starts at open loop poles? Basically, if you can go to the previous slide, and then we can easily see, right, when Kp equal to 0. So, this was denominator, right. So, when Kp equal to 0, this becomes the same as the open loop denominator. So, we had the open loop system, g of s is nothing but 1 by s cube plus s square plus 2s plus 0.1. So, basically now what happens if when Kp is becoming equal to 0, this becomes same as this closed loops transfer functions denominator or characteristic polynomial is becoming the same as open loop transfer function denominator. So, when gain equal to 0, the closed loops characteristic polynomial or closed loops poles is same as the open loops poles. So, because the characteristic polynomial is the same, so the poles are going to be the same. So, it starts at the open loop poles, and then it ends at the open loop zeros. And then the max number of branches of root locus is nothing but maximum number of poles or zeros, because this you can easily see from this thing, because every root locus starts from open loop poles and ends at open loop zeros. No? So, basically like how many number of open loop poles and zeros should be there, how many branches should be there, basically it is maximum of either maximum of poles or zeros. So, whichever is maximum, that many branches we are going to have. Okay. And one thing we can do with root locus is, what if we had a 0 and what if we had a pole. So, that is what we are going to know. So, what we can basically do, we had the g of s is nothing but 1 plus s cube plus s square plus 2s plus 0.1, this is what we had. So, what if we multiply this by s plus 1. So, and then what is the effect of addition of this particular pole is going to have on the root locus thing. So, now something interesting happens, right. So, basically what happens, this is the imaginary axis. So, this is the imaginary axis. If I multiply by a 0, this root locus got shifted towards the that is no, now you can see that there are no poles on the right hand side of the S plane. So, whatever be the gain value you increase, this particular system is not going to go to unstable. So, now one challenge for one exercise for you is like do something with the system so that you can make this, you can for some gain value you can make the system unstable. Not you can add a pole, or you can add a 0, or you can modify, instead of putting a P controller you can try to put some other form of controller that you may know, and then you can try to see like whether at some point this some pole is going to cross this imaginary axis. So, only when this particular pole branch is going to cross into the right hand side of S plane, that is when it is going to go to unstable. So, basically what we wanted you to do is you change the system by adding certain poles or certain zeros, or changing the controller structure from P to PA or something, and then see whether for something it goes into the right hand side for some particular gain value. So, that is what you can do it for yourself. So, just to have fun with this. But this slide, what we are trying to say is, this root locus can be used to analyze like what is the effect of addition of poles or addition of zeros. And one more thing that is normally like when we talk about these poles and zeros, we talk about something called a dominant pole. So, what is this dominant pole? See, everything you can easily visualize when you do this partial fraction thing. So, we are emphasizing the partial fraction thing to understand a lot of control concepts, because like mostly we can imagine, we can actually find out most of the concepts easier when we imagine that way. So, basically when what we say dominant, which pole is going to have a bigger impact on the on the response of the system. On the response of the system, which pole is going to have a bigger impact, that is what we are going to say dominant pole. So, basically let us say we have 2 poles, let us say one pole is say lambda 1 plus say j e power, okay, we will resolve in partial fraction, and then let us assume that we finally found this e power minus lambda 1 t sin omega t plus phi 1. This was the response of first pole. I am assuming you took the partial fraction and then you took the inverse Laplace transform, you simplified everything and you got this particular thing. And the other pole you are going to have I power minus lambda 2 and sin omega t plus phi 2. Now since we have sin, it is like complex poles, okay. So that is what we are going to have. So basically if you can see here, if lambda 1 is higher, if the value of lambda 1 is higher, okay, if value of lambda 1 is higher than value of lambda 2, and since I put minus here, it is clear that these poles are on the left half of the S-plane. So basically we have say lambda 1 somewhere here, and magnitude of lambda 1 is greater than magnitude of lambda 2 basically, so it means that lambda 2 is here. So now if you can see, it is minus 3 and it is minus 2, so 3 is greater than 2, that is what basically it is going to say. So now if you can see here, e power minus lambda 1 t and e power minus lambda 2 t. So which of this term is going to have a bigger impact? So when lambda, since lambda 1 is higher, so what it does is, this particular e power minus lambda 1 t, if you can plot here, it is going to fall like exponentially at a very high rate. So when for the same time e power minus lambda 1 t would be like very less value when compared to e power minus lambda 2 t, because lambda 2 is greater than lambda 1. Lambda 1 is going to pull it down so fast, because as time increases it is going to pull the value so fast. So this is going to die down fast. So when compared to lambda 2, lambda 1 we can neglect. So lambda 2 is the dominant pole. You can actually you can plot this, you can take these two values, you can plot for the same time and then see in MATLAB like how it is responding. So that is one way to do, but we can easily see from max or by intuition, this particular term is going to fall slower, decrease slower, and this particular term is going to fall faster because lambda 1 is greater than lambda 2. So then what we say, this pole is not causing a bigger impact when we in comparison to lambda 2. So lambda 2 is a dominant pole than compared to lambda 1. So the poles that are closer to the imaginary axis is going to have a bigger impact. So that is what, so poles that are closer to the imaginary axis is called a dominant pole. So you can just remember these terms. These terms you may just get someone talking about these terms. So you should not like think like this is something new or something. It's something like very easy to observe when we do the partial fraction thing. So if you want to understand it more, just take some lambda 1 value, lambda 2 value, and then see the response of the system. Okay, so that's what you will be able to see. So to summarize, basically what happens, both lambda 1 and lambda 2 are stable or on left hand side of S-plane. So both are going to fall down. So and if this is how the lambda 1's pole is going to fall down, or for lambda 2 it is going to take much longer time to fall down. So that is what it is going to say. So this is how lambda 2 will fall down. So lambda 1 is falling faster, is getting 0 faster, but lambda 2 is taking it some time to go to 0. So basically lambda 2 is more significant than lambda 1. So it's lambda 2 is dominant pole. That is what we want to say. Okay, fine. Now we are going to ask another question. So what we are going to tell is, okay, given a system, given a transfer function, we are able to tell that what value of Kp the system is going to go to unstable. But in reality, how useful all these things are, okay. But it's something like, given a model which is accurate, we can find the exact value of Kp, the system will go unstable. But we also have seen that all models are approximations, okay. There is one phrase that is actually very interesting, which says like all models are wrong, some are useful. So we are actually looking at some useful approximations of system as model, okay. So whatever we have as a transfer function, like we have a transfer function sq plus s square plus 2s plus 0.1. If this is going to represent say a boiler, okay, I am just taking some random word, okay, boiler, okay. If this is going to be a process and this is going to be a transfer function, then this itself is an approximation. So, with this approximation, if I find a Kp value, we do not know whether we like that particular value of Kp exactly at which it is going to go to unstable. All these things does not make sense when this itself we say is an approximation, right. So, then Kp we can say is like, okay, Kp somewhat closer to 1.9, it is going to go to unstable, but we do not know exactly at what Kp it will go to unstable, how system will behave. Even this is a linear system, this boiler itself may not be a linear system. So, all this, there are a lot of approximations, lot of assumptions. So, in real life we are not interested exactly in finding the value, like exact value of this Kp where it goes unstable, but we are trying to find out what range of Kp it is going to be stable and what range it is going, somewhat like if you can change if Kp is some approximately 1, then we say it is stable. If Kp is closer to say 1.8, then we say it may go to unstable. So, this is a qualitative comparison that we are going interested, not in a so hard quantitative comparison. So, this is when we go for the frequency response thing analysis, which we can see in the future lecture. So, basically what we are going to do is like we are going to take the frequency response analysis what we have done, Bode plot etc., and then we are going to see the effect of we are going to see how this frequency response analysis is going to get useful in stability analysis thing. So, that is what we will see in the next lecture. Thank you.